As a circuit designer, you may want to avoid any faulty nodes in your design as much as possible. So, hopefully, through this video, you may understand why a faulty node or high impedance node check is a must for you either through an inspection or a simulation tool. We'll start to show a few case studies of the faulty nodes, which cause the issue in the circuit and system. Then, we may show you how the industry tool may help you do the faulty node check. The first simple image is a CMOS inverter with an input floating gate. Obviously, both the output voltage or current should be unpredictable since the input voltage is undefined. Since the input gate is floating, the gate linkage may determine the voltage randomly between different chips. Since it's a high impedance node, any capacitive coupling between the floating gate and the aggressor may disperse the voltage on this line significantly. Therefore, we need the input to be well defined. In your Microelectronics 101, you know what a CMOS means. Complementary metal oxide semiconductor. Since the transistor is complementary, the input should control NMOS and PMOS complementary. For example, both inputs are tied to logic 1, and then the output should be 0. Since the NMOS is on and PMOS is off, and vice versa. But if we separate the input of the CMOS, then we should watch out for the off states of both PMOS and NMOS shown here. As you can see, both transistors are off, and the output is high impedance and undefined. So, similarly, the output voltage is defined by the drain to source linkage over drain to body linkage, etc. If this is the case, do you see any reliability issue? Think about the buffer chain image for 5 seconds. Correct. This inverter will connect to another inverter. So, the floating output will be the next inverter's input floating gate. In the first case image, if the floating output settles to a mid-rail, the next stage may have enormous cobalt current. If the metal routing was not wide enough, or the number of via contact is not enough, the metal or via may melt, and the device may also age quickly due to the unexpected high DC current. Besides the current concern, do you see any other voltage concern? Think about a level shifting image for 5 seconds. Correct. For high-speed amplifiers or switches, we may need the core device instead of the I/O high voltage device to either boost the speed or minimize the RC parasitic. On the other hand, for the current source, we may need to maximize the overdrive to either minimize the local OCV or reduce the thermal noise. So, we often may need the I/O device, PMOS current source, on top of the core device, almost underneath. Therefore, it's likely that both the PMOS current source and core NMOS will be turned off in the power down state. Wait a second, that's a power down state, not a mission mode operation. Would that cause any issue if the output is 14? Think about the reliability images for 5 seconds. Bingo! From the 2 slides before, we know that the 14 will settle down to any output voltage depends on the drive phi of the linkage between the I/O PMOS and core NMOS. If the PMOS has a higher linkage than the NMOS, then the output could be 3 volt or 5 volt over the I/O voltage, which is fine for the I/O device. But the core device drain to source voltage is much more stressed than its tolerable 1 volt or below. In addition, the linkage is not zero. Therefore, the high electric field may age the core NMOS quickly, then damage it to break. Besides the reliability issue at the power down, is there any other issue at the normal operation? Think about the settling images in a power saving for 5 seconds. Right, in most applications, we may want to save power and turn off the TX driver in sleep mode if there's no data transmission. Make sense? On the other hand, when the data is ready to send, the TX driver must wake up as soon as possible. In this simplified H-bridge driver, there's a common mode feedback loop to set the driver's output common mode properly over the PVT. Therefore, to stabilize the negative feedback loop, a meter capacitor is a must. From this cartoon image, do you see any issue? Think about the charge image around the capacitors for 5 seconds. Bingo! To charge or discharge the capacitors takes time, which may cause the settling issue if there's a 14 node on each side of the capacitor. A simple overshoot image is shown here. To power down the TX driver, the sensing resistor may be cut off, and then the output common mode is 14 for sure. First, if the output common mode could leak to VDD at the one side of the capacitor, and the OTA output is shorted to ground at the power down state, the capacitor's two sides may be charged to VDD. Second, when we enable the TX, the output common mode voltage will move from the VDD to low voltage since the sense resistance switch is shorted. But again, the voltage across the capacitors is still VDD, and then the OTA output will drop below the ground. Yes, you didn't get it wrong, and it's below the VSS. Third, the whole negative loop is broken without turning on the bottom current source NMOS, such that the PMOS charge the output common mode back to high voltage. Fourth, the OTS output will follow the output common mode voltage between two sides of the capacitor and move up to the NMOS threshold voltage. Fifth, until the NMOS starts to turn on, and then probably the output is nearly VDD. The whole feedback loop starts to work, and then pull the output common mode back to the reference voltage. Lastly, it's obvious that the output common mode voltage drop and up, and then settle down to the right level by taking the extra settling time, which may violate the wake-up time requirements and lose the data transmission. Hopefully, these 14 issues may remind you to watch out your design carefully without missing those 14 nodes. But no matter how careful you are, we might still have oversights easily. Then we may need tool to help. Before checking the floating nodes with the tool, let's come up with a few test cases and see if that works. I put image 1, 3, 5 intentionally as the floating nodes, and image 2 and 4 as the low impedance node. Then I apply the cadence spectre static high Z checker, and that works well to catch the high impedance nodes at image 1 and 3 as shown here. In addition, this checker is very fast since it only checks connectivity issue. Please be advised that it does not require any simulation analysis, but it cannot identify any floating node which happens only during the certain time window of a transient simulation. Next one, with the floating nodes across any capacitor and be caught by the cadence spectre's dynamic high Z option, and it catch the floating variation dynamically. Basically, the dynamic high Z identifies any floating node during a given time window of the transient simulation. Only the floating nodes that exist for longer than the user-defined duration are reported, but the dynamic high Z check is stimuli dependent. Here are the summarized images of showing you why you need to watch out for any floating nodes, and hopefully the industry tool may help you do the floating node check. First, the floating nodes have impacts not only on the reliability issue, cobalt current, or the high voltage stress, but also on the performance degradation, like long settling time during the wake up. Second, the floating nodes can also catch the connection mistakes of your design blocks in an early stage. Third, I demoed the industry flow of the floating node checker through the cadence spectre, but you should be able to apply other tools as well. Lastly, those painful lessons of floating nodes could be avoided with a careful mental image or model. Instead of relying on the floating node check tool, you may want to simulate the ergo state machine image in your mind. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.